Introduction to Systems Thinking. Hello, welcome to this session of Systems Dynamics. In this first introductory video about systems thinking, we're going to talk about what is a system and how systems dynamics was developed historically, and the main characteristics of the topic. This is just a conceptual video, but I'm very enthusiastic because with this we kick off the contents of this course. So let's go. What is systems thinking? In the simplest terms, systems thinking is a mind frame or worldview of reference. We use this mind frame because it explains reality in ways that other methodologies or worldviews cannot address. This worldview has been proven to be particularly useful when dealing with problems of larger complexity with many interacting parts in a dynamic setting. By dynamic, we mean that the values of the parameters and variables that describe the system are changing simultaneously, making the tracking of the system extremely difficult for the human mind. As humans have made progress in the discovery of the rules that govern natural phenomena, mankind has discovered the richness and complexity of the world when all the elements come to be considered together. In this course, we will explore this mind frame and the language that it uses to understand these complex interactions. Interestingly, the same components that are used to understand man-made systems can be used to understand the relation of different actors in nature, as well as different actors in social interactions. We will also be interested in understanding the behavior of systems in general and model them using computer tools. But first, let me tell you the stories of two great contributors to system dynamics. First, Carl Ludwig von Bertalanffy. Bertalanffy was an Austrian biologist known as one of the founders of the general systems theory. This is an interdisciplinary practice that describes systems with interacting components applicable to biology, cybernetics, and other fields. Bertalanffy proposed that the classical laws of thermodynamics apply to closed systems, but not necessarily to open systems, such as living things. His mathematical model of an organism growth over time, published in 1934, is still in use today. In 1972, Buckminster Fuller was asked by a committee of French scientists to write a paper on Ludwig von Bertalanffy's nomination for the Nobel Prize. He did so. The nomination went to Oslo, but the committee's effort came just too late. Ludwig died before the nomination of him could be considered by the Nobel authorities. On June 12, 1972, Bertalanffy died of heart attack. He was buried in Montreal. Systems theory is the interdisciplinary study of systems. A system is a cohesive conglomeration of interrelated and interdependent parts that is either natural or man-made. Every system is delineated by its spatial and temporary boundaries, surrounded and influenced by its environment, described by its structure and purpose of nature, and expressed in its functioning. In terms of its effects, a system can be more than the sum of its parts if it expresses synergy or emergent behavior. Changing one part of the system usually affects other parts and the whole system with predictable patterns of behavior. For systems that are self-learning and self-adapting, the positive growth and adaptation depend upon how well the system is adjusted with its environment. Some systems function mainly to support other systems by aiding the maintenance of other systems to prevent failure. The goal of systems theory is systematically discovering systems dynamics, constraints, conditions, and elucidating principles, purpose, measure, methods, tools, etc., that can be discerned and applied to systems at every level of nesting, and in every field for achieving optimized equifinality. The systems view is a worldview that is based on the discipline of systems inquiry. Central to systems inquiry is the concept of system. In the most general sense, systems means a configuration of parts connected and joined together by a web of relationship. The primer group defines system as a family of relationships among the members acting as a whole. Von Bertalanffy defines system as elements in standing relationship. Some key concepts. Some of the key concepts that you will find in the literature of systems are the following. System, an organized entity made up of interrelated and interdependent parts. Boundaries, barriers that define a system and distinguish it from other systems in the environment. Homeostasis, the tendency of a system to be resilient towards external factors and maintain its key characteristics. Adaptation, the tendency of a self-adaptive system to make the internal changes needed to protect itself and keep fulfilling its purpose. Reciprocal transactions, circular or cyclical interactions that systems engage in such that they influence one another. Feedback loop, the process by which systems self-correct based on reactions from other systems in the environment. Throughput, rate of energy transfer between the system and its environment during the time it is functioning. Cybernetics. Cybernetics is the study of the communication and control of regulatory feedback both in living and lifeless systems, organisms, organizations, machines, and in combinations of those. Its focus is how anything, digital, mechanical, or biological, controls its behavior, processes information, reacts to information, and changes or can be changed to better accomplish those three primary tasks. The terms systems theory and cybernetics can be widely used as synonyms. Some authors use the term cybernetic systems to denote a proper subset of the class of general systems, namely those systems that include feedback loops. According to Jackson, von Bertalanffy promoted an embryonic form of general systems theory as early as the 1920s and 1930s, but it was not until the early 1950s it became more widely known in scientific circles. Threads of cybernetics began in the late 1800s that led towards the publishing of seminal works, for instance, Wiener's Cybernetism in 1948 and von Bertalanffy's General System Theory in 1960. Cybernetics arose from an engineering field and general system theory from biology. If anything, it appears that although the two probably mutually influence each other, cybernetics had the greater influence. Von Bertalanffy, 1969, specifically makes the point of distinguishing between the areas in noting the influence of cybernetics. Systems theory is frequently identified with cybernetics and control theory. This again is incorrect. Cybernetics as the theory of control mechanisms in technology and nature is founded on the concepts of information and feedback, but as part of the general theory of system, then reiterates, the model is of wide application but should not be identified with systems theory in general, and that warning is necessary against its incautious expansions to fields for which the concepts are not made. Cybernetics catastrophe theory, chaos theory, and complexity theory have the common goal of explaining complex systems that consist of a large number of mutually interacting and interrelated parts in terms of those interactions. Cellular automata, neural networks, artificial intelligence, and artificial life are related fields, but they do not try to describe general, universal, complex, singular systems. The best context to compare the different C theories about complex systems is historical, which emphasizes different tools and methodologies from pure mathematics in the beginning to pure computer science now. Since the beginning of the chaos theory, when Edward Lorenz accidentally discovered a strange attractor with his computer, computers have become an indispensable source of information. One could not imagine the study of complex systems without the use of computers today. Systems dynamics. Systems dynamics is an approach to understanding the nonlinear behavior of complex systems over time using stocks, flows, internal feedback loops, table functions, and time delays. According to a page in Social Systems Design Lab of the Washington University in St. Louis, systems dynamics is a method for understanding, designing, and managing change. It models the relations between elements in a system and how these relationships influence the behavior of the system over time. For example, how do aspects of culture, livelihood, education, and environment impact the adoption of new public policy or prevention or treatment program? Convenient graphical user interface systems dynamic software developed into user-friendly versions by the 1990s and have been applied to diverse systems. Systems dynamic models solve the problem of simultaneity mutual causation by updating all variables in small increments in positive and negative feedbacks and time delays structuring the interactions and control. The best known system dynamic model is probably the 1972 The Limits of Growth. This model forecasts that exponential growth of population and capital, with finite resource sources and sinks, and perception delays, would lead to economic collapse during the 21st century under a wide variety of growth scenarios. Systems dynamics is an aspect of systems theory as a method of understanding the dynamic behavior of complex systems. The basis of the method is recognition that the structure of any system, the many circular, interlocking, sometimes time delay relationships among its components, is often just as important as determining its behavior as the individual components themselves. Examples are chaos theory and social dynamics. It is also claimed that because there are often properties of the whole which cannot be found among the properties of the elements, in some cases, the behavior of the whole cannot be explained in terms of the behavior of the parts. This is what we call emergent behavior. Systems dynamics was created during the mid-1950s by Professor J. FORRESTER of the Massachusetts Institute of Technology. In 1956, FORRESTER accepted a professorship in the newly formed MIT Sloan School of Management. His initial goal was to determine how his background in science and engineering could be brought to bear in some useful way on the core issues that determine success or failure corporation. FORRESTER's insights into common foundations that underlie engineering, which led to the creation of systems dynamics, were triggered to a large degree by his involvement with managers at General Electric during the 1950s. At that time, the managers at GE were perplexed because employment at their appliance plants in Kentucky exhibited a significant 3-year cycle. The business cycle was judged to be insufficient explanation for the employment instability. From hand simulations or calculations of the stock flow feedback structure of GE plants, which included the existing corporate decision-making structure for hiring and layoffs, FORRESTER was able to show how the instability of GE employment was due to the internal structure of the firm and not to an external force such as business cycle. These hand simulations were the start of the field of systems dynamics. During the late 1950s and early 1960s, FORRESTER and a team of graduate students moved the emerging field of systems dynamics from hand simulation stage to the formal computer modeling stage. Richard Bennett created the first systems dynamic computer modeling language called Simple. Simulation of Industrial Management Problems with Lots of Equations, in the spring of 1958. In 1959, Phillips Fox and Alexander Pugh wrote the first version of DYNAMO, dynamic models. An improved version of simple and the system dynamic language became the industry standard for over 30 years. Forrester published the first and still classic book in the field titled Industrial Dynamics in 1961. From the late 1950s and the late 1960s, systems dynamics was applied almost exclusively to corporate managerial problems. In 1968, however, an unexpected occurrence caused the field to broaden beyond corporate modeling. John F. Collins, the former mayor of Boston, was appointed a visiting professor of urban affairs at the MIT. The result of the Collins-Forrester collaboration was a book titled Urban Dynamics. The urban dynamics model presented in the book was the first major non-corporate application of systems dynamics. The second major corporate application of system dynamics came shortly after the first. In 1970, J. Forrester was invited by the Club of Rome to a meeting in Bern, Switzerland. The Club of Rome is an organization devoted to solving what its members describe as the predicament of mankind. That is, the global crisis that may appear sometime in the future due to the demands being placed on Earth's carrying capacity, its sources of renewable and non-renewable resources, and its sinks for the disposal of pollutants, by the world's exponential growth of population. At the Bern meeting, Forrester was asked if system dynamics could be used to address the predicament of mankind. His answer, of course, was that it could. On the plane back from the Bern meeting, Forrester created the first draft of a system dynamics model of the world socioeconomic system. He called this model World 1. Upon his return to the United States, Forrester refined World 1 in preparation for a visit to MIT by members of the Club of Rome. Forrester called the refined version of the model World 2. Forrester published World 2 in a book titled World Dynamics.